All right, you might remember from the previous video we talked about how doping, introducing a small impurity into the crystalline lattice, changed the electrical properties of the material. So on this side, the N-type, we've got free electrons, and here on the P-type, we've got free holes. What happens when we put these two together? Well, something very interesting happens, but we need to simplify our diagram. First of all, it's way too complicated. So we're going to go for a diagram that looks like this. We're only going to show the electrons that are free to move, and we're only going to show the holes that are free to move. Of course, there's electrons in the whole lattice work here and atoms. We're not showing all of them. We're trying to simplify it down. Well, what actually happens when we put these two pieces together? Well, just thermal energy means these guys are buzzing around. One's going to fall across that P and N junction and fall into a hole. Remember, a hole's like a little energy well. Imagine a marble rolling into a little well tile. It's going to get trapped there. It can't move anymore. So all of a sudden now we've got a hole that can't move because it's filled, and we've got an electron that can't move because it's fallen into one of these holes. We've now no longer got free charge carriers. We've created a region in here which we're going to call the depletion zone. It's depleted of charge carriers. There's not the charge carriers that there used to be there. The other interesting thing about this is that this side of it becomes electrically negative. Can you see why? Because everything was electrically neutral to start with, but now electrons have come across into the P junction, so I've got minus charges, negative charges that weren't there before. And of course, similar logic means that the other side of the depletion zone is going to be positively charged because it's now no longer got electrons that were there when it was electrically neutral, so it's gone from neutral, it's lost electrons, that's going to make it positively charged. Okay, so let's connect this device up into an external circuit, and you'll have to bear with me because it's going to seem like nothing particularly exciting happens. I'm just going to put the charge across the depletion zone up the top there so we don't get confused with the field generated by the battery. The whole point of this device is to generate a device that allows electrical current to flow in one direction only and not the other direction. So first of all, we're going to look at the direction in which it can flow, a forward bias diode, and the direction in which it can't flow, which is a reverse bias diode. Now, why is that exciting? Well, you just have to believe me, it's exciting, because once you can rectify, once you can make current only flow one way, you've created one of the three really critical things that you need to be able to do to make any kind of electronic circuits, like the computer that you're watching this video on is full of diodes, and so we need to be able to make them. Okay, so if I connect up my battery in this way, what is the battery doing? Well, the battery is basically taking electrons from the positive side and through a chemical reaction, depositing them onto the negative terminal of the battery, which creates this push, this electrical field, which is going to cause electrons to move around the circuit. So we push suck another electron from there, this electron from here, they're going to be spaced out, it's going to push all these guys around, it gets a little bit tedious. So basically we're pushing more free electrons into the N-type semiconductor, which means these guys here, as we start to build up their numbers, they're going to be pushed over towards the depletion zone, and as they move towards the depletion zone, it's no longer a depletion zone because there's now free charge carriers there. And remember that we probably really shouldn't be showing these guys here because they're actually not free charge carriers, they're just part of the ordinary lattice. So let's get them out of our diagram because we're only showing free charge carriers. Okay. What happens on the other side here? Well, remember this battery is pulling electrons and shoving them from the positive to the negative terminal, which is going to create a field, electric field, which is going to pull the electrons in this way, and it's going to create a bit of a desire for electrons over this side. Remember, the whole lattice is filled with electrons already. And if there's enough energy provided to it via the electric field, this electron, the electron, is going to move into here. Look, we've suddenly got a free hole that we didn't have, which is going to migrate towards the negative side over here, which means we've got holes migrating into the depletion zone, which means the depletion zone basically disappears because we've got holes and electrons being pushed into the center of this PN junction. Okay, what happens then? This electron falls across into the hole. Now, it doesn't get annihilated, but in the sense of being a free charge carrier, we've now just lost an electron in a hole. But remember over this side over here, electrons are being pulled out into this wire here, creating a new hole. The battery is going to pump that electron across into here, which is going to push everyone along one and put the electron back here. Look, we've still got the same number of free charge carriers. And so a current is able to continue, it's able to be sustained, because every time we fill up a hole with an electron, and so they kind of cease to exist in the lattice. Over here, an electron's being pumped out of here, pumped into the battery, and going and appearing over here, and we've got a new hole and a new electron. New hole, new electron, they get annihilated. Over here, electron gets pulled out around the external circuit, pushed into here, hole migrates over this way. So the whole process is sustainable. We can carry a charge. An electric current will flow clockwise through this diode, or the electron flow, if you like. The electron flow is going to be moving from the N section to the P section in this diode. And let's have a look at what happens when we reverse the bias, when we turn the battery around. Now all of a sudden we're pushing electrons from this side of the battery and sucking them into the positive side, as it were, pushing electrons here, which means we're trying to push electrons into the P-type semiconductor, and we're sucking them out of the N-type semiconductor. So now electrons are going to come in and jump in and fill a hole. Well, I haven't got a hole anymore, so I haven't got those free charge carriers. That hole is no longer free to move. And over here, we're pulling electrons out of it, okay, because remember, we're sucking those electrons and pumping them onto this side, pushing them into here. So now I've got less electrons over here than I had before, and the electrons are coming around and filling up holes. So now they're no longer existing as free charge carriers. Can you see what's happening to my depletion zone is getting wider and wider and wider, okay? Because the holes are going to migrate in this direction, because that's the negative side of the terminal. Electrons are going to migrate in this direction because that's the positive terminal that's connected to the battery. So our charge carriers are migrating to either side of the PN junction, which means that the depletion zone is getting greater. But that's not sustainable, because once we annihilate our last two charge carriers from there, our depletion zone effectively is now the entire crystalline lattice. The whole thing is now an insulator. We've run out of free charge carriers to move, and so the current will stop. And the current only runs for a infinitesimally tiny period of time at any rate. So effectively what we've got is we've got a device that allows electrons to travel that direction across the junction, but not in that direction. They can only travel from the N-type to the P-type, and that is what a diode is. And if you're wondering why that's exciting, see one of the other videos.